Okay.
She's sick anyway.
Ava, thank you so much for sticking with us through all this setup. Maybe you're somewhere else right now, but it is started, if you can hear me.
Yes, thanks for
thank you all for bearing with me and us as we set up this room. Thank you, Dr. Rostami, for finding this available room at the last second. This is my PhD proposal. Just for all of you that might not have met me before, my name is Austin. I'm a PhD student in the mechanical engineering department. I have a background in electrical engineering, and I got my bachelor's from North Dakota State University, and then my master's here from Colorado School of Mines in electrical engineering. And today I'm going to be talking to you about my proposal. And as the title says, we're focusing on material and wear classification techniques for underground mining. And specifically, we're looking at load cells and acoustic sensors as the primary vehicles for this research. So underground miners are exposed to many hazards, and they have many duties that they need to perform. In particular, coal miners are most at risk. They're 50% more likely to suffer an on-the-job injury and account for 50% of fatalities from 1983 to 2020. For this work, we're focusing on finding ways to help them infer material and tool wear, because these are two of their primary duties that they have to perform. And these tasks can be difficult to train. Right now, experienced operators will simply use acoustic, visual, and even vibrational cues from the environment to deduce material and wear conditions. So as I said, this is really difficult to train. It can be somewhat subjective. Operators will all have different cues that they know to look for. And it's a very dangerous job. Of course, the machines themselves can expose them to crush hazards. There's been a recent uptick in black lung cases recently. And of course, the tunnel itself can collapse or explode, which is very dangerous. And so we want to find ways to put instruments into this environment. And so that itself is difficult because of the harsh environment. There's very high forces in the rock cutting operations. As I said, there's explosive gases. You can expect that anything you send into this environment will likely be consumed. And so it needs to have a low replacement cost, and it needs to be easy to replace. And additionally, it's difficult to deliver resources to this environment in general. So power consumption needs to be low, and communication bandwidth also needs to be low, because it can be difficult to do that communication underground in a tunnel. So as I said, the miners have many duties. Safety is, their number one goal. And other people have tried to help them with some of their other duties. And so we'll talk about those first, and then I'll talk about what duties we're focusing on for this part of the research. So to talk about a bit what's been done before for the miners, obviously there's personal protective equipment. This is generally considered the least effective strategy because it only mitigates the most immediate hazards. The most effective thing that's really been implemented has been the personal proximity detector. And what this device will do is it will instrument personnel, and then as the machines approach them, or if they approach the machines, and if they enter certain keep out zones, this will disable machine operation in that area. And this was released about 10 years ago, and that coincides really with a sharp decline in fatalities and injuries, especially regarding machines. Other things that have been done have been looking at changing how the miner has to work, trying to offload some of their cognitive load. And one example of that is a hydraulic monitoring system, which will monitor the hydraulics of the system and maybe raise an alert if there's a diagnostic issue that needs to be treated. But this can free the operator's attention to focus on, frankly, some of the more exciting tasks that are happening as they're cutting. So if we look at what's been done and what is recommended to do for hazardous situations, the CDC, NIOSH, they have a way of recommending things that you should do. You can see at the bottom of the list is personal protective equipment. So we saw examples of that. We saw examples of administrative controls with the hydraulic monitoring system. And an engineering control would be the personal proximity detector, which will actually intervene just in time to prevent something hazardous from occurring. So we want to look at how we can move to the higher parts of this pyramid. We want to get to substitution. We want to get to elimination, ideally, because that's going to be the most effective thing we can do, is actually eliminate the miner being in a hazardous situation. We want to take them further away and maybe see if they can do their job from a more remote location. So the thing that's really been the most in this direction has been the remote operation of the machines. And what this has really done is allowed the miners to work more efficiently. They're able to collect better feedback from the environment. But what this has led to, and this has been noticed in the literature, is that the miners, the operators, will typically put themselves in a more hazardous location to try and get this feedback, and that'll lead to injuries or other operational mistakes. So this can maybe be considered a substitution control or maybe engineering because you're changing the situation, you're moving the operator further away, but this one hasn't really increased safety, it's just made mining more efficient. So if we look at all the technology that's been put in place in these underground mines, we notice a trend. Most of these technologies only aim to assess hazards as they're occurring or right before they occur. It's a diagnostic system. What we want to do is we want to move to a prognostic system, which is going to enable us to look at the actual process variables as they're happening and then perform our cutting in an efficient way that's going to avoid these hazards in the first place and eliminate the hazardous conditions by moving the miners further away from the cutting interface. So that's what we want to do. We want to help operators work safely and efficiently, and we believe we can do this by moving them away from the cutting interface. What's preventing this, a gap in the knowledge, is that there hasn't really been too many material and wear classification techniques specifically for underground mining. This is frequently done in other industries that we'll talk about, but we need to bring these technologies to underground mining. This hasn't been done yet. And another thing is we need a sensor to measure some of these things so we can determine material and wear categories. And we'll talk about what we can look for to identify material and wear next. So specifically, what we're going to do to look for material and wear is we're going to investigate this hypothesis. We say that there are vibrational mode changes correlated to changes in tool wear and material conditions in rock cutting that are detectable in the 0 to 200 hertz band and in the 20 hertz to 20 kilohertz band. You might recognize that second one as being the human acoustic range. And so we're going to, for sure, investigate acoustic sensors. The lower range is a good range for force sensors. And so we'll talk about how we're investigating both of those frequency ranges. And to do that, we need to build a sensor. And so far, if we break this research into 3 aims, we've been able to take the sensor that we've been working on and identify tool wear, classify rock type, and the thing that we're still working on is being able to estimate cutting forces. Of course, we're still improving upon these first 2 aims, and then I'll show you what exactly we're doing for the 3rd aim. I'll go through the first 2 aims together because it turns out the methods for these things are actually very similar. And then after I talk about how we're doing our classification schemes, I'll talk about how we're developing the sensor that's going to provide the data for some of these classifications. So first, the first 2 aims, like I said, we want to detect modal variations from material and wear conditions using acoustic or force sensors. And what this is going to enable is it's going to enable the operators to perform their role from a greater distance because they're not going to have to look for these feedback items in hazardous locations. So if we look at what's been done for material and wear estimation in other domains, we can see that this is very popular in the oil and gas industry, as they're also very interested in determining what they're cutting through and how worn their tool is as they're drilling for oil. It's very common to use vibrational or acoustic data for some of the same reasons. It's really known that different materials are going to break apart differently. That's been long established. And also the different tool wear levels, because they have different geometries and different shapes, you're also going to have different modal responses from their interaction with the rock. So that's what we're going to look for, and that's what these other techniques look for, is changes in the modal response. And one example of this would be an acoustic sensor in steel milling. We can see that this here is the mean distribution of the frequency spectra. And we can see that there's some pretty clear differences based on tool wear level. And this is, of course, caused by changes in tool mass and geometry. Some benefits of acoustic sensors, they're pretty low cost. You can use pretty general designs. You generally just stick a microphone somewhere close to where you care about. And it's also well known that these different process conditions are going to make different sounds. And this is very intuitive. You've probably likely heard most of this before. Specifically, we have knowledge that different materials are going to take different energies to break apart. A guy named Teal in 1965 had his seminal paper, Specific Energy in Rock Cutting, and he stated that if you have a certain volume of rock and you want to break it into a certain size piece, based on the material, it's going to take a certain amount of energy to do that baseline, and that's the specific energy of the material. So in a way, we're expanding upon that idea by not just looking at the energy, which is correlated to the average force, we're actually looking at the frequency response. And so not just the DC component, but all the other frequencies as well. Similar to materials, we know that there's differences caused by tool wear, because that changes your tool geometry, your tool mass, and so your vibrational modes are going to change. It's known that worn tools can take 3 to 5 times the force, specifically the conical picks that we're looking at. And there's been some recent attempts to use stuff like video or even acoustic and radio information, but these are much more recent developments, and 2 of these technologies can be susceptible to interference. Specifically, in this video example, which was published in the April issue of the MME journal, he noted that you get interference from the dust particles, but you can still look at the color and the intensity of the pixels to get the values that you want. So some of these other technologies take a bit more of a removed look at doing this material and wear classification, but we want to get close to the signal source with either a force sensor or an acoustic sensor. And if we look at the different kinds of sensors that are typically used for material and wear estimation, we notice that for our requirements, specifically for underground mining, acoustic and capacitive sensors stand out pretty well for meeting most of their requirements. Strain gauges are also useful because they're what's implemented on our experimental platform, and they are known to provide good linear measurements under your laboratory conditions. So they're going to serve as a reference for these other 2 sensors a bit. And so these are what the sensors look like. As you can see, we have an acoustic sensor, which is just a microphone. And the bottom right, we have a strain gauge. And then in the top right is our custom sensor. And we can see its integration with the steel case and the tooling. So we're going to be using all of these different sensors to collect information from our rock cutting experiments. And what we're going to do with that information is we're going to put it through a vibration classification scheme, which if you look at the literature, that's how these problems are referred to in general. And these typically lend themselves to standard signal processing techniques. I've listed here the ones that are most popular and the ones that we're going to be investigating. For example, you can take a fast Fourier transform of your input data to look at the modal responses. And then you can take that frequency data and put that through your machine learning classifier. And that's really the most common way to come out with these modal classifications. And we know from the literature that doing this pre-processing generally improves accuracy, and so we're just going to do that right away in our analysis. Again, like I said, we're looking for modal variations caused by changes in material structure or tool geometry and mass. We know that this should be detectable with acoustic sensors, 1, because that's what the operators use as part of their classification scheme. And then 2, we also know that it should be doable with force sensors based on a large body of research that says different rocks take different amounts of energy to break. And like I said, we're going to pre-process these things. The samples that we're going to do for this study, we've already cut 3 of them. We've done concrete, limestone, and sandstone. We have a coal sample planned for early this summer that we're going to be cutting with our improved sensor design and also the same sensors that we've been using for the other blocks. We're going to be cutting these blocks with different wear level picks. So we have a new pick, a moderate pick, and a worn pick. The new pick is unmodified. The moderate pick can be considered about 50% through its useful life. And the worn pick should really be thrown away at this point. It's done with its useful life. So you can see, if you're not familiar, that these picks fit into this block, and then that block goes on this continuous miner, which is the machine we saw at the beginning, which cuts through the coal wall. But for our experiment, we're going to be using this linear cutting machine. And it has strain gauges integrated on the platform. It uses hydraulic actuators to push the rock block against the tool to cut through it for our full-scale rock cutting tests. I have a video of it in action here. you can see it cuts through the rock. Also shows all of my YouTube recommendations. And so again, these are the sensors that we're using on the cutting machine. Strain gauges are integrated with the platform. We have a microphone mounted nearby, and then this tool is integrated directly on the pick. The sensors directly. Yes. And so we're going to take this data from these sensors, and we're going to pass it through these different combinations of classification schemes. So we picked the most popular ones. We're going to try all the combinations. So that's going to give us 27 classification schemes in all that we're going to be able to compare and see really which ones work best for our application. And it might sound like a lot, but we're going to do this over the next 2 years. And also the way that we're implementing these, once we have one of these implemented, it's very easy to use that processing pipeline to use the other techniques with the ones that we've already developed. And to compare all these different techniques, we're going to use the F1 score, which is a very popular classification metric for these schemes. It's roughly going to answer how many did it get right from 0 to 1. More technically, it's a ratio between the precision and the recall, where you can think of precision as the number of targets hit out of attempts, and you can think of recall as the number of targets hit out of total targets. I don't know if I said precision the first time, but precision is the first one, recall is the second one. And so it's a ratio of those two things that gives you a score from 0 to 1. And if we look at the signals that are going into the classifier, we can see if we split them apart by material, for example, concrete and limestone, then teams can get upset. Okay. So we can see there's pretty clear differences between the two. Concrete, in general, has lower primary modes than the limestone, and also the decay from these modes is more exponential in shape, where limestone we have kind of this bumpier characteristic. If we look at the signal split by tool wear, we can see that these features are actually much greater in magnitude, and that there's a clear difference between the signature of the new tool versus the signature of the moderate or the worn tool. And even though the moderate and worn tool appear more similar, we can still see differences. If we look at the worn tool, we can see that these modes are, on general, a little greater than the modes for the moderate tool. So it's kind of easy to see how we could take a signature and then maybe classify it into one of these categories. And the computer can see these differences too, can do this classification. So to start, we've implemented the support vector machine because this was believed to give us the most useful results going forward. It has a good balance of hyperparameters. It doesn't have very many, so it's still quick to implement, but it's a little more sophisticated than k-nearest neighbors, which, if you don't know, k-nearest neighbors will simply take your input signal and then compare it to its library of training signals, and then whichever ones it's closest to, it's going to pick that as the majority class. The support vector machine is a little more sophisticated than that. It'll actually transform the input data to a much higher dimension in an attempt to get some better separation of the data. So you can typically expect better results from a support vector machine. So we've implemented this one first. We didn't choose the feed-forward neural network right away because it has a large number of hyperparameters. So it can take a longer time to implement properly, and it can be more prone to overfitting, whereas the support vector machine is generally general in these problems. And it's also been very popular for other material and wear classification problems in other industries. So if we look at how this first classification scheme performs, we can see that we get some acceptable results. Here we have the F1 score for material ID. We can see it about 80%. Tool wear, it does about 90% on the F1 score. And we can actually see that most of our confusion in tool wear, so if you're not familiar, these are confusion matrices where the diagonal entries are going to be your correct classifications. The off diagonals are going to be errors. This first column is your prediction, and all of these columns are the actual state. So most of the confusion is between our moderate and worn picks, which makes sense because when we saw the signatures earlier, we saw that those two were much more similar to each other than the new tool. If we look at how the acoustic sensor compares for tool wear, we can see that it scores similarly with an 85% F1 score. And we can notice that It doesn't have as much confusion between the moderate and worn picks, but it also isn't able to pick out a new pick just as well. So this might be indicating something along the lines where the force sensor is actually closer to the process and it's able to pick up some of these details a bit better. And it also speaks to the fact that looking at information from different sources can give you a better picture. And something that we might want to investigate is combining these information sources in different ways to see which one gives us the best benefit. Also, if we look at this classification scheme's score based on its test train ratio, we can see that the classifier is somewhat generalizable. Even if we give it a very small percentage of training data, it still scores acceptably well, somewhere in 70%. Of course, as we add more data, it's going to do better, but we don't see the performance just immediately degrading, and we also don't see it scoring a perfect 100% on the classification. So this is letting us know that it's very likely not latching on to something in our data, and that it's actually doing the classification based on something that would be useful to use in the actual application. So with that, that covers the first two aims, the material and wear classification. Now we're going to pivot and we're going to talk specifically about the development of the force sensor. And so this custom sensor is what we used, what I called the capacitive sensor in the previous two aims. We'll see that it doesn't have superlinear measurements. And what we want to do is there's a large body of research in underground mining for models which leverage cutting forces and rock pick interactions and geometry and things like that. So we want to be able to use those models still, which work well. But to do that, we need a force measurement. And so we need to have a force sensor that can do this. And specifically, we're going to be comparing two different capacitive load cell designs. And I'll talk a bit about why we choose capacitive load cells. The short of it is they fit our application really well. If we look at what's been done before in underground mining for sensors, we see that, again, most of these sensors aren't really suited for force measurement. These are trying to measure the surrounding conditions. So if we look at things that are normally used for force sensors, there's a couple typical examples. The first one that might come to mind is resistive. These are what strain gauges are. And how a resistive force sensor normally works is you have a very small wire that's going to change length as you deform it. And as the length increases or decreases, this is going to change the resistance of that wire. Some problems with this is you normally need to be sending current through the element if you want to make a measurement. This can draw a lot of power. The wire is also basically an antenna, so it can be susceptible to interference if you don't shield it properly. There's an intrinsic link between temperature and material resistance, so you can compensate for that in different ways, but you're still going to have these problems with a resistive element. Two, the little wire can be kind of delicate if it gets scratched by something wrong, and we know that this rock cutting environment is going to be very high force, very abrasive. Another technology that's popular are piezo sensors. These are a bit better on power consumption and robustness. The primary drawback is that you need pretty specific materials for these types of sensors. And another one is that these materials are generally very brittle. So if you expose them to too great of a force, it's going to crack and your sensor is going to be done. So that leads us to capacitive sensors, which are actually a more recent technology. Publications in capacitive sensors have increased 17% year over year since 1990 something. So they're becoming more and more popular, and there's reasons for that. They're very low power, they're very robust, the designs can be very general. So if we talk about those a bit more, we can see that these types of sensors are normally used in harsh environments. One example is you can have a silicon carbide capacitive sensor, which will actually go in a jet engine to detect the pressures inside there. But generally, the design is pretty low cost. You really just need two conducting plates and then something that's not conducting, and then you have a capacitive sensor. So the design is very general. We're choosing this parallel plate design in the bottom left because out of these other designs, it's known to be more sensitive since the plates are closer together. And it's also very robust to interference because these plates basically provide their own shielding and all of the sensing is happening inside this dielectric region, as opposed to these other configurations where you have maybe an open-ended design or a tilting electrode design where you're actually looking at these fringing fields. This parallel plate design, all of the field strength, most of the field strength is inside that dielectric. So that's not going to be exposed to too many different things. And there's no intrinsic relationship between temperature and capacitance, unlike resistance. So if we look at capacitive load cells, one really interesting thing that's enabling low-cost applications is that you can embed these load cells inside flexible printed circuit boards. So this technology meets our requirements. It has low power consumption, it's robust, it's low bandwidth because it's our force sensor, and it's very low cost to produce. One of the main drawbacks is that modeling of these flexible materials is an active research area. There's no really established literature on exactly how these materials are going to deform under all circumstances. We know that they're nonlinear, and so we can ask, okay, what does this look like, really? This is one example of characterization of polyimide dielectric load cell, our same materials and design. And we can see that it's very typical that lower loading rates are going to lead to greater displacements. That's just how the material behaves. And we see too that at our higher loading rates, we get less displacement. And two, as the loading rate gets higher, the peaks tend to get closer together, and it's not really significant as much that they're different anymore. So we can look at kind of the same characterization for our sensor. Here I've split apart that previous diagram, which is more of a hysteresis plot. This is the triangle loading. So we load the sensor and then we unload the sensor, and this is the response we get. And we can see that we really get what's supported by the literature. We have lower loading rates leading to wider swings in displacement. And we see that as our loading rate increases, our peaks get closer and closer together. This is especially true for very thin films that are in the micrometer range. At this point, we've entered the range of mesomaterials, and so your molecular interactions are actually going to dominate over your bulk properties, which you might see maybe in the millimeter range or greater. And this is caused by the polyimide is actually made of these long polymer chains. It kind of looks like a plate of spaghetti, and they're all just squished in on each other, and they'll rotate and slide and twist. And so this isn't really a linear deformation that we're seeing. And we do know that it's dependent on the load rate, just based on empirical testing and existing literature. So if we want to put that graph in the same way, we can really compare and see that these things are, in general, the same. The only difference is that here they zeroed all of their starting, and here we zeroed, we didn't zero our starting. But we can see that the lower loading rates are, of course, giving us wider swings in displacement. And again, these higher loading rates are appearing similar. If we look at the data from a rock cutting experiment through our custom sensor, we can see that we are not capturing the linear forces, which is our aim for this sensor. We are able to do material and wear classification, and we can see that the dynamics of the sensor are actually giving us separation in tool wear. And we believe this is correlated to changes in the mean force, which are present. This will basically capture the mean force, which is going to be different between the new moderate and worn tools. And so we have some separation there. But if we want to move this sensor to being a linear sensor, which is going to give us force measurements, what can drive these existing models, which are very prevalent and accurate and useful, we need to change up the configuration a bit. So on the left side, we have the cutaway for the thin film design. And we can see that all of the sensing is happening in this tiny region in between the plates. And so that's what's leading to the greater sensitivity of this design, is because any movement is going to squish these plates together. And since they're so close together, your capacitance is going to change by a large amount. But since the material's so thin and so nonlinear, we're going to have nonlinear deformation. To improve upon this, we can take the same steel case design and just change the capacitive plate design. We're going to use this single-ended plate, which is in a way going to measure the volume of this cavity through the capacitance. And in doing so, this cavity is going to deform much more linearly than this other cavity, because we're really only using this steel case as the agent of deformation. And we know from our earlier characterization that the steel case actually deforms really linearly. It is just this squishy polyimide that's causing these nonlinear measurements. So the only drawback of expanding our sensing region is that we are going to have lower sensitivity, just because our capacitance isn't going to change by as much because it's a bigger gap that's not squishing as much. So what we have been able to do is develop a very cheap and nonlinear load cell, which is still useful for material and wear classification. It's under 2 millimeters in height, and the unit cost for the prototypes was less than $100, assuming you have a laser welder. The cost for operating your laser welder are marginal. It only takes 20 seconds to laser this thing together. But as we said, this design isn't really suitable for linear measurements. So we're working on testing our improved air gap design. We've scheduled the load frame characterization for this sensor for the middle of May, May 17th. And this is going to be in preparation for rock cutting tests, which, as I said, are going to occur early summer. So from that, we'll be able to know if this other design has the properties that we anticipate that it does. Based on all of this work, all 3 aims, we're going to split the work into 3 journal articles. We've collected experimental data for the first 2 articles, and experiment number 3 is planned and coming up very shortly. We have a platform for our custom load cell. We've also investigated some other sensing technologies that are useful for the first 2 aims. And based on all of this, I should be able to graduate by the end of 2023. If we look at a simplified version of the schedule, we can see that coal cutting experiment occurring later this year. That's going to lead into paper 2 and paper 3, drafting my thesis. And I shouldn't be doing too many things at the same time as I'm trying to accomplish all of this. And so with that, I'd like to say thank you all for bearing with me through this long presentation. And what?
The elephants in the roof.
Yes, and the elephants in the roof. And open the floor to any questions.
So we'll have questions from the audience at large, and then we'll ask our observers to step out and questions for you. Ask you to step out, and we'll bring you back in. It's a whole bunch.
Yes.
I'm curious with the tool wear classification specifically, you selected 3 categories for the new, moderate, and worn. I was wondering if you considered like a continuous variable, if that would be useful, and then if your SPM approach could handle that, or if you had to do a different approach, or what? Maybe just discuss that for a second.
Yeah, that's a really good question. There are some existing models that have tried to use force measurements to maybe have a continuous wear indicator. If you do it in that scheme, it's much different from a typical machine learning classifier, which is normally looking for these discrete categories. You can do it with something like a feed-forward neural network. You can still set it up to give you like a 0 to 1 indicator of wear level. One issue with this is it would be difficult and expensive to test because you'd actually have to wear through and cut an entire pick to get these continuous wear levels, which it would really take a large volume of rock to cut through with a linear cutting machine. So we need to be creative in how we set up that experiment. But it has been done, it has been investigated. Most of those models actually end up using the force and then integrating that somehow. Thank you. Yeah.
Yeah. So one of the things you presented earlier was you were saying when you had a worn tool, you had a force of 3 to 5 times X, right? The higher than initial. Is there for people in industry or the people that are out doing this mining, when do they typically want to change the tool? Like how worn does it have to be? Like is it, and that's related to his continuous curve. Like is it 100% worn, 87% worn? Because you have more force when you're operating it, that costs you more money. And then obviously, is this a single pick? Or is there an array of picks operating at the same time? Is it one tool only?
That's a good question. In the application, there is the continuous mining machine, which has all of those teeth on it. It's that big drum.
Right, I think I remember, yeah. Then if you have that, then when you make the choice of stopping to replace the pick, right? Is it if one of them are worn, or that's a complicated mesh to look at?
What they'll normally do is they'll replace them at the end of shifts or at the end of the day because it's not really efficient to stop to just replace 1 or 2 picks. And then I think that might lead into another question, like how many of these picks do you want to instrument on the application? And it depends on what you want to do. If you want to simply assess material conditions, you could probably get away with instrumenting like every other pick, every end pick. But if you want to do per pick tool wear, of course, you would need to instrument each and every pick. But the low cost of this sensor is required so that you would be able to do something like that.
I have a question on the capacitive sensors.
Yeah.
So it's a very high fatigue load, right? You looked at life cycle or sensor drift over time.
That's a good question. To limit fatigue in the sensor, the idea was to limit deformation to several percent, like no more than 10% worst case scenario of the steel case. So that was really the strategy for mitigating fatigue, is only do small range deformations. And that really should be enough to also protect the sensing element itself. With this air gap design, we actually won't be exercising the polyamide anymore. It'll all be in the steel case. And so as long as that is able to wear at a rate, significantly lower than the tools and be useful for maybe multiple tools in a row, or even just a single tool, depending on how low the cost is. That's the idea.
So would you be looking at replacing the sensor every time you replace a tool?
Ideally, no. But if the sensor were cheap enough, like if it was a fractional cost of the pick, maybe something like that could be worth it. Thank you. Yes.
One last question. So you kind of mentioned you have a few different measurements, like the acoustic and force and capacitance. And you briefly mentioned, but have you looked into combining those with sort of some sensor fusion? Or I think you maybe mentioned that this is future work. I'm just curious if you can discuss that a little bit more.
That would be future work. That's more planned for Article 3, where we'd actually do a comparison of most of these methods. But yeah, the idea would be that you could take, your frequency signature from your acoustic tool and the frequency signature from your force tool, and then just give both of those concatenated to your support vector machine. And then it should be able to classify those assumedly more accurately, since there's more information. But
so you could basically, in your analysis, it seems like it'd be easy to plug those into and see if you get a significant improvement or not, and then assessment.
Right.
I have lots of questions. Do you want me to wait, or should we just, what do you feel like?
Either. We have go committee, questions now. If you're done. So let's thank everybody for coming, support and option.
Yeah. Thank you. I'll end the meeting.
Good luck.
Thank you.
Yeah, so,